Did you correct me? Okay, welcome back everybody. We are at now Lecture 3, and we are trying to work on Section 2.5, Linear Functions and Models. I believe I had this up at the end of the last lecture where we had our objectives listed. And our objectives listed here are the easy part, graph a linear function. We want to look at a couple applications. I think we have about 3 of those. I think we have all agreed we know how to distinguish a linear function from a nonlinear. You tell me. How do you look at the equation and know that it's a line? How do you?
The exponent for x is 1 and the exponent for y is 1.
Okay, the exponent on the x is 1, the exponent on the y is 1. You've got to at least have a y in there. Now, you might not have an x, but you got to at least have the y. And the power has to be to the first power. And that's how you're going to recognize the linear. Okay, and then we want to talk a little bit about direct variation, which I'm actually going to call one of the applications to the linear function. At the end of the last class, we did not finish the Are You Prepared section, the Are You Prepared section. So we still have problem number 4 to go over. We ran out of time. But now that I understand how number 3 was being worked, we're going to back up and look at number 3 again, just to clean it up from last time. Okay, everybody with me and we're good? All right, so here's our objectives today. 2.5, our linear functions. Finished the Are You Prepared? We're going to review graphing the linear function real fast and look at our applications. Then we're going to move into the library of functions, and let me put stars beside this in red. This is a must. This is a must. These are going to be the basic functions that you're going to need to know how to recognize so that when we build on these functions through transformations, we will have a great idea what the graph of the function looks like. We can discuss it. So 2.6 is the basis, so we have to know that. Okay. I want to back up, though, to section 2.5, Are You Prepared? We did this in the last lecture, but we're looking at number 3 because I was not quite following what was happening, but now I know. We're told that the slope is -3, and the line contains the point -1, 5. And you were asked to write the equation of the line with slope -3 and passes through the point -1, 5. And the direction my brain went was, this is a very easy point slope form, which is y minus the y coordinate equals the slope times x minus the -1. And there's an equation of a line that's perfectly great because the problem didn't say it had to be in any particular direction. Okay. But when I gave it to the group, your brain went a different direction, and I had trouble following it. So here was the direction I was trying to figure out what was going on at the end of class. You started out saying, I know that the slope is the difference in the y's over the difference in the x's. And he's going to use this to come out with slope-intercept form, which is a perfectly great way to do it if I had followed what was going on. So he put -3 for m, y minus the y coordinate equals x minus a -1, which became a +1. All right, so everything's great so far. And then he said, I know that in this equation, I already have the -3, so y equals -3x. I already had that piece of information. But now I need the y-intercept. So the y-intercept is the ordered pair 0b. The y-intercept has to be a solution to this equation. So what he did was he came over here and said, well, that must satisfy this equation. So he went and said, I need to solve for b. So -3 equals y is b, x is 0, plus 1. Do you see what he's doing? He's looking for a way to solve for b. Okay, so now we have negative 3 equals b minus 5 over 1, which of course we know is just b minus 5. So when we add 5 to both sides, which have negative 3 equals b minus 5, add 5 to both sides, we're going to get 2 is equal to b. So then his equation in slope-intercept form would be y equals minus 3x plus 2. That's a perfectly great way to do it. And if you followed this part down solving for y, you would get minus 3x. Negative 3 times 1 is negative 3, and when you add 5 to it, you have 2. So both of these are the same answer. He just had a different approach. I wasn't quite sure what was going on. Perfect. You're perfect. All right, everybody good on that? So 2 ways to do the same thing. 2 ways. All right. The fourth question that we didn't even look at in Are You Prepared was to solve this equation. This is called a linear equation. It's not called a function. You don't see any y's in there, do you? It's a linear equation in one variable, x. And this is just reviewing. Do you remember how to solve a linear equation? So here's the work that was turned in. The problem was 6x minus 900 equals negative 15x plus 2,850. So I love the way the work is shown here. It's making correct mathematical statements. You're communicating exactly what you're doing, which is so perfect. It's very clear that you added 15x to both sides of the equation and added 900 to both sides. There were no steps skipped there, so we know exactly what's going on. Your goal was to solve for x, so you got all the x's on one side. 6x plus 15x is 21x, and that looks like if you add those two numbers, that's 3750. And then you were so good to show every little step. Math is more than just an answer. It is, can you communicate and express what you were doing? So you showed us that you were going to divide both sides by 21. And then you punched it in the calculator. Your question is, where should you stop rounding? Well, if you're on a test and you're not using a calculator, which I don't expect many of your tests to have calculators except for the application parts, I would be happy with you to just stop right there. If it said express to 2 decimal places, you would stop right here. If it didn't say, you just ask me. Okay? Or you just do what you can. If the test doesn't say, keep going. Okay? But usually on tests for things like this, it would be a non-calculator question to begin with, and this is perfectly fine. I'm more interested in, do you know how to get here? Because anybody can go punch that in a calculator. Okay? Everybody good? Excellent job. I'm going to give you a big check. Perfect. Perfect. Now you can't read your work, can you? There you go. Thank you so much. All right. Let's begin then the real material in 2.5. And we'll take about 2 seconds graphing that linear function. The first objective.
What about 4?
Excuse me?
What about number 4 on Are You Prepared?
That was number 4 on Are You Prepared?
Oh.
Okay. All right, we're in 2.5. And we're talking about graphing y equals mx plus b. And you've already studied this as a line, but we're in the section for functions, so we may think of it as f of x equals mx plus b. All right, we know to recognize a line because it has a y to the first and it has an x to the first. It doesn't always have to have an x, but it must have a y. Because y equal to b, what would be the graph of y equal to b? What does it look like? For any number b, what's the graph going to look like? Straight line, horizontal straight line. Y equal 4, y equal 3, whatever, horizontal straight line. So, and that's still a function, right? Still a function. So we recognize it's got a y to the first. It could have an x to the first, but it can't have like x squared or y squares or x y's or anything like that. Okay, we've looked at graphing some, but let's look at graphing like y, which is a function of x, is equal to minus 2/3 x plus 4. Let's see if we can graph this. Now, this is a section in graphing techniques, so sloppiness is not allowed. You label your axes. Label your axes. Everybody repeat it.
Label.
Or guess what will happen?
Um,
A point off, because we're looking for good graphing. Okay, you got to indicate what your units are, and you got to be consistent. Now we know that the units on the x-axis and the y-axis, the y-axis could be by tens and the x-axis by ones, but you just got to indicate what they are so that you know. Okay? All right. This will be a half a second problem, I'm sure. What's the first point you're going to plot on here? You're going to plot negative 2/3. Is that a point? The B is the y-intercept. So I think we're going to want to plot 4. How'd you get negative 2/3?
Because I was saying to go down 2 and over 3 and then put the point.
Okay, but where were you going to start?
Oh, at the origin.
Okay, but the origin is not a solution there. You have to start at your y-intercept. Okay, so mark that in red in your paper so you don't forget. All right, so we're going to start here. Now I'm ready for your response. We have a slope negative 2/3. So instead of rising 2, we're just going to drop 2. Drop 2, that's negative. And we're going to run 4. 1, 2, 3, 4.
3.
What?
3.
Wrong. 3. That really is not there. Pretend it's not there. We're going to drop down 2 and run 3 correctly with your help. All right, so that means the point 3, 2, 3, 2 should be a point on the line. Whoops. Okay. All right, now how can I check very quickly to make sure that I didn't make a mistake? All right, we can substitute in here to make sure that's true. Remember, you say, is 2 equal to, I put that in for y, negative 2/3 times the x, which is 3, plus 4. Negative 2/3 times 3 is negative 2. Negative 2 plus 4 is 2. So it checks, so we know we have the correct point. Okay, how would I find the x-intercept? How do you find the x? All right, remember you let y equal to 0. So we'll have 0 equals negative 2/3 x plus 4. Okay, and we want to show all the steps just like you're telling me to do. So we're going to subtract 4 from both sides. Okay, and now to solve for x, we're going to multiply by the reciprocal of negative 2/3, or it's also called the multiplicative inverse. Remember all those words? We're just doing unto one side of the equation as you do unto the other. So a negative times a negative is a positive. 12 divided by 2 is 6. So x is equal to 6. And you will notice that if I had been continuing on here, whoops, there's 5. This would be 6 right here. I believe my line would have been perfectly going through the 6. All right, everybody good with x and y intercepts? We're happy, aren't we? All right, we're good with linear. Let's go with some applications. You have basically 3 applications we want to talk about, and these are in your book. So we're going to say application number 1, and that is going to be called straight line depreciation. Okay, if you are running a business, and you have business expenses for your income taxes, when you purchase a piece of equipment, you're going to be able to depreciate your equipment over a period of time and write it off as an expense on your income taxes. And many things are just straight line depreciation. this would be like computers for your business. The Internal Revenue Service will let you depreciate it over 5 years, and then you've written off the cost of your computer. And we're going to take an example similar to that. What we're going to do is buy a computer. Now, you don't get to write it off for personal use. It's only if it's business use. Buy a computer that cost $1,500. And if I'm not mistaken, I believe that the Internal Revenue Service allows that to be a 5-year depreciation. So we're going to say it's going to be worth $0 in 5 years. Okay? All right, we want to write a function that gives the value, and I'm going to call that V, of the computer in T years. Okay? We want to write a function that gives the value of the computer in T years. By the way, if this computer is only going to have some value for 5 years, what's my restricted domain? 0 to 5, right? 0 years is when you buy it. 5 years is when it's worth nothing. So you're only interested in between 0 and 5. Does that make sense? All right, so let's just draw this and see what it looks like. They're telling us that it's a straight line depreciation, or at least your book does. Along this axis, we have T years. Along the y-axis, we have value. Value of the computer. So we'll mark off our units 1, 2, 3, 4, 5. And along the y-axis, we will put in some units. I think I'll go 300, 500. Whoops, not. How about 600? I'm going to do by 300s. 600. The next one would be 900, 1200, 1500. Okay? Like I said, the units on the y-axis don't have to be the same as the units on the x-axis. All right, the information that we have is that when we first buy the computer, which would be today, the value is $1,500. We're told that it's going to be worth $0 in 5 years. And we're going to have a straight line depreciation here because somewhere in the problem it had to tell you that. Although my little words right here didn't tell you, but that's the topic. So straight line, let me see if I can draw somewhat a straight line through here. Yeah, a straight edge would be too easy. There you go. That's somewhat of a straight line. All right. Now if we look at the graph, we can sort of guess what things are. Like it looks like at the end of 1 year, the value of the computer is something like close to $1,200. 2 years. Looks like I did pretty good picking up my units there. All right. But our question is to write the value of the computer in terms of T years. We want V of T. All right. So we already know this is a line. You know, we usually think of it as y equals mx plus b, equation for a line. What's the slope here?
It would be 300 over 1.
How do you easily determine a slope?
Isn't it 1 over 1?
Excuse me?
It's 1 over 1 on that one, isn't it?
Well, let's see.
Negative 1.
Isn't it
Oh, yeah.
Don't I have 2 points?
Negative 1 over.
Negative.
Negative. Well, the line certainly is going down, so we expect it to be negative. All right. How do you normally find a slope? Slope is change in y over change in x. And I'm given 2 definite points. I have the point 0, 1500, and I have the point 5, 0, right? Is that correct? All right, so we can just go right here. The change in y, 1500 minus 0, change in y's, over the change in x's, 0 minus 5. Okay, 1,500 minus 0, 0 minus 5. Okay, so this is 1,500 divided by negative 5, which is negative 300. Okay, all right, so we've got part of our function written. It's got to be v of t equals the slope. Well, our slope is negative 300. Instead of x's, we're using t's. Okay, and now I got to get the plus b part. And b is your y-intercept, so that would be 1,500. Okay, so I have written a linear function where the value is a function of t, the t years after the computer is purchased. And we want to remember that 0 is less than or equal to t less than or equal to 5. We have a restricted domain here because I guess if you kept going, that means that somebody would have to be paying you money. I'm not sure if you went below the line there. All right, questions? Once you've got this, it's very easy to see what is the value of the function at 3. Means after 3 years, what is its value? So that's negative 300 times 3 plus 1,500. Negative 900 plus 1,500, which looks like that must be 600. And so if you go up 3, there it is, close to 600 anyway, supposed to be. All right, I want to go back though. I want an interpretation. I'm big on interpretations. I want us to interpret the slope. Interpret the slope. All right, and my units is change in y. That means change in the value, which is money. And change in x is change in years. All right, years. So if you see negative 300, how do you interpret that slope based on what the problem is? Let's hear some. What do you think? Negative 300 what? Okay, excellent. That didn't take you long to interpret it. For this computer, the value of the computer is going to be going down or dropping $300 per year. Okay, so negative 300, the value of the computer, value $300 per 1 year. Because you can think of that as negative 300 over 1 drops $300 per year. Everybody got it? Okay. Suppose the question asks you for this problem. Let me turn the page if I can. V of t equals negative 300t plus 1,500. Okay, pretend the question asks you when will the value of the computer be $800. What am I looking for?
What? How many years will it take it for it to get to $800?
Okay, when is a time, so we're looking for t. Looking for t given, now what's this $800? It says the value of the computer is $800.
The value after
V of t is 800. All right, let's make sure everybody translates the words, because word problems, everybody usually goes, oh, don't know how to do them. But it says value of the computer. This part right here is value of the computer. When says I'm looking for t. And when the value of the computer will be, or I could say is, in math is equal 800. Does everybody see how you translate it? Okay, so now all we have to do is say, well, what is V of t? We've got negative 300t plus 1,500 equals 800. Now we're just going to solve the equation. So of course I'm going to subtract 1,500 from both sides. 800 minus 1500. So negative 300t is equal to negative 700. So t then is negative 700 divided by negative 300, which is 7/3, which is equal to what? 2 1/3? What's my units? 2 1/3 what? Years. Okay, what's a third of a year? 4 months. So it's going to take about 2 years, 4 months, because 1/3 year, 1/3 of 12 is 4 months. So it take about 2 years, 4 months before the value of our computer is $800. All right, straight line depreciation. You're given 2 points, write the function, answer the questions about it. Any questions, anybody? Are we good? Did I make it look easy? That's my job. Can you do it on your own, though? That's your job. All right, the next application, very important for your business and liberal arts calculus, also for your economics classes. One of my favorite little topics. So this is application 2. And this is called the supply and demand. Supply and demand application. Who's had economics and you've talked about the producer supply? Yes. And the consumer demand. See, I didn't know that related to math, did you? Okay. I'm going to start out with the question, and then I'm going to get all the terms in here together. All right, when we talk about a supply, we're really talking about the producer's supply. The producer is running a business, and based on the price of the item, the producer will supply so many units. So along here we have the number of units that the producer will supply. Okay, now if you're running a business and the price is near $0 versus if you're running a business and the price is $100 per unit, when are you going to produce the most units? If you're receiving $0, let's say you get $1. Okay, you're going to make those old Beanie Babies. Y'all grew up with Beanie Babies, didn't you? Didn't you have Beanie Babies? If the Beanie Babies started out at $5 a piece, right? And then people started wanting them, and they were paying $20 and $30 for a Beanie Baby. Okay, well, didn't all of a sudden the supply start really coming out because the producer was going to get a lot more money? So basically, when you have a producer supplying something, they're not going to supply too many units when the price is close to $0.
Wouldn't it just be smarter to supply less food units when it's at a higher price? That way you can charge even more.
Say it again.
Wouldn't it be smarter to supply less units at a higher price so you could charge
Well,
more?
you got to get the consumer to buy it. This is in terms of supplying stuff that the consumers will buy. All right, so if the price is low, they're not willing to produce as many units. But as the price gets bigger, the producer will produce more items. Does that make sense? So the price is high, they're going to have more revenue coming in. All right, then we have what is called the consumer demand curve. The consumer's demand. Well, normally, if the price is low, the consumer will buy more. For example, going to the movie theater. If the price per ticket is $3 to $5 versus the price per movie ticket $25, you're going to have more people who can afford to go at the 3 to 5 versus the 25. So the higher the price, you start losing some of your market. When the Beanie Babies, I heard some of them went for like $500. No way I was paying $500 for a Beanie Baby. I was not sure I was paying $5. Okay? All right, so when the price gets really high, The consumer is going to buy less because you're losing the market, just like for basketball and football tickets. Everybody can't afford those tickets. Okay, so the consumer will use more units when the price is low, and we're just doing linear applications. Now, consumer and supply curves are not always linear, but they are in this particular section of the book. All right, but we're working with linear. So if they're free, all of you would probably run to the movies if it was a new release and it had all the right actors and actresses in it. But as the price of the ticket goes up, this is the price of the ticket going up, the consumer will have less demand because they can't afford it. Okay? So this axis right here is number of units for the producer and for the consumer. Now, where these two curves intersect, in economics you call that you said you already had this, what do you call it?
I don't remember.
Equilibrium.
Equilibrium point. Okay, and I have my own word for that, and I'm expecting it to show up in a textbook sometime or another. I call this the happy point.
The happy.
Happy point. And I'll tell you why. I think happy point sounds better. What happens is, this is the point where the producer and the consumer are both happy. The producer is willing to produce this many units at this price, and the consumer is happy to buy this many units at this price. Everybody is happy, and so you've reached a point. There are people who would pay a higher price. There are times that the consumer would produce more at a lower price. But at this place right here is the happy point. The consumer will purchase and the producer will supply, and we're all happy. Okay, but your book and every economics book calls it an equilibrium point. All right, then you're going to study more in calculus that's called a surplus, consumer surplus, and that is an application of integration in calculus, but you will study this. All right, so let's take an example. And we have numbers. I don't know how realistic they are, but the numbers work really nice. We're going to say, given that we have the producer, and I'm going to put that in parentheses because your book will just call it a supply. But I want you to keep remembering it is the producer who's going to supply. I think sometimes that makes it easier. We're given that the supply function is S at P, where P is price, equals 1/2 P plus 2. P is price. P is price. We're going to be given the consumer, and that's called demand in your book. Demand. And we'll call that D at P. Okay? And the equation for that is minus 5, 6, P plus 10. Okay? And let me read the words out of the book like you're going to be seeing when you get these. I'm just reading some words out of the exercises. Suppose that the quantity supplied and the quantity demanded are given by these equations where P is the price. Find the equilibrium price for the example. Find the equilibrium price. Okay? All right, let's get a picture of this. Should have done one in red. We'll do consumer in red. Okay. All right, so let's see if we can graph this. Okay, along the x-axis, I'm going to put what? Price. This is dollars. And along this axis is units. Number of units, and then we would have our demand. Okay, because when the certain price, that will be the amount of the supply. All right, and along this axis, looks like I need to go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and we'll mark off some units this way and hope that I come in good here. 2, 4, 6, 8. Okay? All right, so the first thing I'm going to do is graph the supply curve. The y-intercept is 2, so we got a 2 right here. And the slope is a half, so we'll go up 1 and carefully run 2, up 1, carefully run 2, up 1. Graph paper would really help, wouldn't it? Run 2. Whoops. Run 2. Whoops, my units got off. Ooh, that's bad. Make that dot bigger. All right. Okay, this is my supply curve. This is the producer supplying. Okay, and let's do the demand curve. The y-intercept is 10. That basically says if it's $0, the consumer will rush right out and get 10 units of this. If the price is $0, this producer will supply 2 to test the market, but nobody, that's all they would be willing to do. All right, the slope is -5, 6. I'm going to carefully try to come down 5. 1, 2, 3, 4, 5. And I'm going to try to run over 6. 1, 2, 3, 4, 5, 6. Woo, how nice. Let me see if I can draw that. Okay, and this is the consumer demand curve. Okay, now my graph was so good it looks like I found the answer to my question. We're looking for the happy point. I'm going to convince everybody it needs to be called happy instead of equilibrium. But this is the point at which the consumer will purchase, the price at which the consumer will purchase their number of units, and the producer will supply. Okay, but of course your graphs are not always perfect, so how do I solve these equations to find their point of intersection? How do I algebraically solve this for the equilibrium point? Okay, method of substitution sounds good to me, so let's flip the page. We want to solve for the equilibrium point. And where the two curves intersect, that means the supply curve has to be equal to the demand curve. The supply curve is 1/2 P plus 2. The demand curve is minus 5/6 P plus 10. Okay, everybody see where I just copied that from? All right, so now we have a linear equation in one variable. And the first thing all of you are probably doing is looking at this and going, yuck, it has fractions in it. Anybody say that besides me? All right, personally, I like to clear out the fractions so I don't have to worry with common denominators. What can I multiply through by that will eliminate all the fractions? 6. If I multiply through both, it's an equation, do unto one side of the equation as you do unto the other, you can eliminate the fractions. The common denominator for 1/2 and for negative 5/6 is 6. So I'm going to do unto one side of the equation as I do unto the other, multiplying both sides by 6. Usually if I have an equation that has a fraction in it, the first thing I want to do is get rid of the fractions. So 6 times 1/2 is 3, so we got 3p. And 6 times 2 is 12. Equals 6 times negative 5/6p is what? Negative 5p. And then 6 times 10 is 60. Everybody good? All right, now we're going to do, I'm going to try to do it as neat as you did when you did your warm-up. I'm going to add 5 to both sides. And I'm going to subtract 12 from both sides, trying to get p on a side by itself. So 8p is equal to 48. So now we're going to divide both sides by 8. Just do it like this. and we have P is equal to 6. Okay, our ordered pair is P and the number of units. Okay, so this is not all we need. We know the price we need. The price is 6. Now we need to know the number of units that are associated with that. Okay, but how do you do that algebraically? Just substitute it into either one of the equations. Just do like either one that you enjoy doing. I think I'll do the first one. So we'll say S of 6 equals 1/2 times 6 plus 2. 1/2 of 6 is 3. 3 plus 2 is 5. So this means that the consumer is willing to purchase 5 units when the price is $6 per unit. It also means that did I just say consumer? The producer is willing to produce 5 units when the price is 6. Everybody's happy. Questions on that, anybody? All right, consumer and producer surplus. All right, can you see? Everybody good? All right, so that's our second application, the supply and demand curves with an equilibrium point. All right, the third application, which is pretty simple, I don't know really why it's at the end, is called direct variation. Application number 3 is called direct variation. And the words are y varies directly with x when it's written this way. This is in your book on page, so you'll know your book here. Let me stick it. Page 249. Page 249. Let x and y denote two quantities. Y varies directly with x. That's the way we like to say it. Or you could say y is directly proportional to x. For any non-zero number k is y equals kx. Y equals kx. Okay? Varies directly. Which looks a whole lot like just a linear equation where we've been calling k what? Slope m. Okay? So it's just if k is greater than 0, all we have is the graph of a line that goes up. It's got to go through the origin, 0, 0, correct? All right, so let's just name a couple things that we know varies directly. What kind of things go up like this? If you go through 0, 0. How about revenue? What's revenue? That's a term you got to know for your business calculus. It gets used all the time. What's revenue?
Profit.
We have words like revenue, cost, and profit. So revenue is not profit. What is revenue? You're running a business. What's your revenue at the end of the day?
The money you save.
The money you,
Save.
not saved, not a good word.
Actually made.
The made sounds like profit. Earn that day. Okay, that's closer. Revenue is the amount of money you have coming in that day from sales. It doesn't mean you made that amount, which means that's profit, cash in my pocket. It just means, okay, you're running a store and you sell socks. And if you, along this axis, you have number of units, which might be socks. Along this axis, you have the price that you charge. Of course, you don't have this part over here. So that day, if you've sold nothing, you have no revenue at the end of the day, no money in your cash register. But if you sold 3 pairs of socks that day, whatever the price of those socks were, that's how much money you have. So if they're $2 a pair, 3 times 2 is 6. Revenue is the amount of money coming in from the sale of your items.
So it's gross value.
Gross. It is gross. Right. Okay, what is cost?
The amount it costs.
What kind of things go into cost?
Without profit?
Okay, yeah, you're not
Wow.
considering the profit. You're running a business. How do you determine your cost?
I guess it would be like advertising and
The
paying your employees,
Overhead.
that type of thing.
Yep, and what else?
Overhead.
Overhead, okay, and
What you pay
then
for it, the shipping.
shipping, all that stuff, and also how much it actually costs to make the item,
Yeah.
right? The cost to make the item.
Whatever.
Okay, so cost generally has two things in it. It has fixed cost plus variable cost. The fixed cost is exactly what you said, the overhead, paying your employees, getting your building, buying your equipment, all that kind of stuff. The variable cost is actually what it takes to make one item, two items, three items, four items. Okay, so if I were trying to do a direct variation, I would be ignoring, in my example, fixed cost, and it would just be on a variable cost basis. Okay, that means free overhead. All right. The next word is profit. You have some questions in your exercises that involve these words, and it's very important for your calculus. Now, how does profit relate to revenue and cost when you're running your business?
The revenue
Difference
minus the
between-
cost.
Exactly. Profit is revenue minus cost. Revenue minus your cost. And you definitely hope that you have more money coming in from the sale of your items than what it cost you. Okay? Usually, again, you have that fixed cost, so a cost function usually starts below the x-axis because you're already in the hole when you start and you got to sell some items and eventually you get above the line. There's another term in the exercises called break even point. What do you think the break even point is when you're running a business?
When your revenue and profit are the same thing.
Revenue and profit are the same?
Cost and
Cost and
profit.
Okay, two ways to look at it. You can say your profit is equal to zero. When you're breaking even, you haven't lost anything, haven't made anything. Or if you use what profit is, that is revenue minus cost equals zero. Or you could say revenue is exactly equal to the cost. That is where you have your break-even point. Okay? All right. Something else that's direct variation. It could be, for example, if you're looking for some things, going to the gas pump. That was my example the first day, right? If gas is $2 a gallon, $2 a gallon. If you don't pump any gas, it's $0. Every time you pump a gallon, it's $2, $2 more dollars, $2 more dollars. So an example of direct variation would be purchasing gas. Another example that I've seen somewhere is hair growth. The hair on your head, I think, is supposed to average like a half an inch a month. Is that right?
It goes a lot faster than that.
Yeah, on the average, I think I've read somewhere your hair grows like a half inch a month. So wherever you're starting, then you would be able to see how much your hair grows because it's going to go up 1/2 inch per month. That's your slope. K is your slope here. All right, direct variation. Are we good? All right, let's go to the exercises in the book pretty quickly. We're on page 252. Nope, we're on page... Which page do I want? Yeah, it is page 252. Page 252, I want to look at problem number 48. And this is a cost function. Okay, notice I told you, talked about you would have some revenue functions and some cost functions. These are terms that you're going to be seeing in your exercises. I particularly like this one because it involves chocolate. You pick your problems based on what you can relate to.
Okay.
All right, the cost C of chocolate-covered almonds. And I really like chocolate M&Ms with nuts in the middle. All right. They're peanuts, right. Chocolate-covered almonds. I really prefer the peanuts. Okay. Varies directly with the number A, where the number A is pounds of almonds purchased. All right, so first thing I want you to do is write a function that relates the cost C to the number A of pounds of almonds purchased. All right, so I'm going to skip the little middle part. I want you to find that linear function that relates. Notice the word varies directly. All right, check your neighbor. Be sure you're using the right symbols. I see you guys smiling. Do you not have it on your paper? Get busy. Point at them because they're not doing their work. Cost varies directly with the number A, which is pounds. All right, so cost is what? K times A, right? You're just translating the words. Cost varies directly with pounds. Everybody got it? Just read the words. Varies directly. Okay. If the cost is $23.75, $23.75 when the number of pounds of almonds purchased is C. Do you try not to mumble because it's picking up on the tape and that interferes with them hearing me. Okay. If the cost is $23.75 when the number of pounds of chocolate purchased is 5, now we're going to be able to do what? What's that going to allow us to do? It's going to allow us to find K, isn't it? All right. So the cost is, so we have 23.75. Cost is $23.75 when you purchase 5 pounds. That's going to allow us to find out what the K is. So K then is equal to, what's that when you divide by 5? 4.68. I'm trusting you. I don't have my calculator. So there we have C equals 4.68 times A. So now we have our formula for the direct variation. All right, basically, somebody tell me what that K really means in words.
Cost per pound.
Price per pound, exactly. Remember, that's a slope. That's a slope. MX, M. That's a slope. And you have cost. This is money divided by 5 pounds. So this is the cost per pound. Right, so now we know the cost.
It's
Yeah.
$4.75.
Yeah, it's
Oh, I did the wrong number. Sorry.
I forgive you. I made a mistake once. All right, thank you very much. All right, $4.75 per pound. $4.75. Thank you for correcting that. All right, so the price per pound is $4.75. Now we're ready to finish the problem. Everybody good on that? Okay. Find the cost when the number of pounds purchased is 3.5. The number of pounds purchased is 3.5. Where do I stick in a 3.5?
Next to the 4.75.
Okay, that's number of pounds. So we're looking for the cost when the number of pounds A is 3.5. And somebody multiply that out for me.
16.65.
It's what?
16.625.
1665. So if you bought 3.5 pounds of these chocolate-covered almonds, the cost would be
It actually rounds to 63.
63.
You missed me too.
$16.63. Okay, everybody good? All right, we're going to stop here and pick up the next lecture. We'll probably look back and make sure we hit all the terms, and then we're going to move into section 2.6. All right, go take a break. Okay, we're going to continue on now with Lecture 3B, and at the end of the last lecture, we didn't get a chance to flip through the pages in the book to make sure we're on top of everything. Then we're ready to go into section 2.6, and do you remember what I wrote in Lecture 3A about 2.6? Very, very important. Yeah, that was the first lecture. I didn't label it A, but it was really 3A. And then we're going to make sure we're very good with the library of functions, and then from those functions we're able to use them and go into some graphing techniques and graph some pretty interesting other graphs using horizontal shifts, stretches, compresses. Don't worry, we won't get to all of it today. Vertical shifts, stretches, and compressions, and reflections. So library of functions are the basis for this. All right, I want to just put 2.5 in front of the camera, and let's make sure we covered everything. Don't forget you're supposed to be wearing out your textbook. We talked about linear functions. Everybody was good with that. I didn't mention average rate of change of a linear function, but I felt like we did that so much before. Average rate of change, that's just your slope of your line, change in y over change in x. Don't forget to put your units with it. Remember yesterday we did miles per hour. Watch your units. Then we looked at the application, straight line depreciation. The next application we looked at is supply and demand. The producer supplies, the consumer demands, and you find a happy point called the equilibrium point where you're at a price that the producer will supply and the consumer will purchase. Equilibrium point is here, should be called happy point. Okay, we did not do objective 3, which is scattergrams, so we'll just kind of turn the pages on through that. We briefly talked about the difference between linear and non-linear relations, and clearly looking at a picture you can tell if it's kind of linear or not. Straight lines. Linear means straight. Objective of the course is not using a graphing calculator. And then the next thing we talked about was direct variation. Y varies directly with X. And let's make sure I covered everything in the exercises. I'm on page 251. Here's equations with problems with supply and demand. Down in the middle is a break-even point. We talked about what is revenue, what is cost. Break-even is when revenue equals cost. We just discussed that in the last class. Remember, profit is revenue minus cost. Very important words. Your problems have straight line depreciation questions, cost functions, some revenue functions. I don't see anything with profit functions, but profit certainly is something that you want to understand what that is for your calculus class. Okay, so I think we're good at 2.5. Don't you agree? You're perfect. All right, let's move on into 2.6. We have two objectives to cover in 2.6, the library of functions and the piecewise defined function. So the first thing we're going to do, just like always, is go to the end and make sure we're prepared. We only have 3 simple questions on page 262, and we'll just divide up so everybody doesn't work so hard. I'm going to let you 4 group together over here and do number 1. Let you right in here, be sure to turn around and include her, do number 2, and you guys over here on the end, number 3. Okay? Are you prepared for section 2.6? And do it on a piece of paper I can bring up here and let's look at it. Say thank you, because if I make a mistake, I want it pointed out on this camera. Okay? So Robert, you just feel free to turn around and talk to those guys behind you.
Do we have to do like an absolute graph or just a general one?
A very good graph. No sloppiness in this class.
But it says sketch.
I'm saying make a good sketch.
So I have to like put all the numbers where it actually crosses the numbers. Even though it doesn't actually get.
Make a good sketch of the graph.
You know which bracket it should be.
No fair using the calculator. No calculators. I know that's your security blanket, but you can't use it. All right, do I have number 1 ready?
Sorry, it's right there.
Is that a very good sketch?
No.
What is it?
You do it, so then you could show them what counts.
Okay.
We have to like work it, or we're just drawing a picture.
I want what you think is a very good sketch of that, and then we'll talk about it.
But we need to plug the points in then.
Y'all decide what you
We
need.
can do like 4.
Y'all got one for me?
Our graph is 1 over x. We don't have to actually put numbers in it, do we?
I want a very good
But
sketch.
it's asymptotes. It doesn't
Ah,
cross.
4,
It's not
then
definite.
that would square root to 2.
I want a very good sketch.
And then that can be our point, I guess, before it.
Which one's going to be used? Yours? Okay. Do I have number 2? Number 2?
Well,
Number 1? Okay. Am I going to take yours?
Mine might be a little smaller to read.
Okay. I'll get out my glasses. All right, we're waiting on number 2.
Well, like if the x was equal to 1, so 1 over 1.
Change, like make 0, make the x 0.
Then
Just make it by
0
then
minus
2. So 1 over 2 y equals negative. So it's like right there.
Okay, give me something.
Okay, 2 just drop.
That's your x. They do the same thing with y. Like when you put
Okay.
Shut up.
All right, I'll take this. Okay, let's go over these and see how we can, if we agree and if we need to improve on anything. All right, let's see if we can focus in on this one. This was number 1. Sketch the graph of y equals the square root of x. And we're going to be critiquing this because we want to make sure we're all good mathematicians and are very careful with everything we do. When I first look at this graph, do I see anything missing on the graph? Okay, we didn't label the axes. Let me do it in red so you guys don't forget. And ladies, label our axes. Okay, and we need to indicate some units here. They do look consistent though, that's very good. Okay, and then what I like is that you plotted a couple points to verify what it was. You have 0, 0, and if you wanted to set up a little chart, when x is 0, y is 0, that's this point right here. And you basically did this over here when x is 4, y is 2. And this is going to be part of our library of functions. And we're going to be using this to create other functions. So I'm going to write on here. We're usually going to have at least 3 key points when we graph. So the other one that's real easy is the point 1, 1, when x is 1, y is 1. So for our graph of y equals square root of x, it looks like a half a parabola. Looks like half of a parabola on the side. And some key points are 0, 0, 1, 1, and 4, 2. So when we see y equals square root of x, and even when we're going to move it around, by shifting up, down, left, right, stretching or whatever, we're going to keep up with those 3 key points. Okay, so I'm just going to give y'all a check instead of a check plus, because you didn't label your axes. You sort of got away with the units because you labeled a point there. So, you know, I could have figured that out. All right, we're good there. Let's go. Everybody happy? Let's go to problem number 2. Problem number 2 says sketch the graph of y equals 1 over x. Okay, things look good here. We got an x and we got a y. That's the start. Let's label a couple point coordinates here. Units. We got a 2 here, negative 2, negative 2. So we need to get some units on our graph when we're going to make a good sketch. Let's call that good sketch. All right. Now let's make sure that everything is matching up. It is clear, just like you were saying, your domain, check that out first, is x could never be equal to 0 because we can't have division by 0. And in fact, x equal to 0 is going to be called a vertical asymptote. And if x can never be 0, y can never be 0 either because 1 divided by a number is never 0. So the x-axis is a horizontal asymptote. Okay, so we also want to be able to keep up with a couple of key points here. And an easy one, of course, is when x is 1, y is 1. So you want to be sure that it goes through the point 1, 1. Okay, I'm going to say that probably it was my mistake. This was probably supposed to be 1 here and 1 there so that it intersected right there. Correct? All right. So if this were 1 and that was 1, we're not too far off. But you want to be sure you have 1, 1. And you notice that if x were a half, 1 divided by a half is 2. So you know that the curve is going to get real close to the y-axis. Or when x is 2, the y value is a half. So it's going to swing. You got the shape. Oops, it's not going to hit the x-axis. The shape is correct, but we do want to look at a couple key points. And for sure, 1, 1 is a key point. And the same thing with negative 1. Negative 1 is a key point. Negative 1, negative 1. And it's going to approach those asymptotes. Okay? All right, pretend that part's not there. That was a slip. Okay, so if I had labeled my units correctly, they were not units of 1, then I would have been okay. All right, everybody good? All right, can anybody tell me what kind of function this is called? It has a name.
Reciprocal.
Reciprocal function. This is called the reciprocal function. What was this one called? Square root function, and this one's called the reciprocal function. Okay? All right, and then we have the third problem. The third problem was to list the intercepts. So we're looking for first the y-intercept. So when you have y-intercept, you let x be 0, y is equal to -8. Check. Okay? And when you were looking for the x-intercept, you let y equals 0. And if you have x cubed equals 8, your answer is correct, but what is it that you do from this step to this step to solve for x? How do you get rid of that cube exponent? Take the cube root of both sides. So you basically took the cube root of both sides. Another way some people look at it is instead of using a cube root, you use the fractional exponent. So you could say x cubed raised to the 1/3 power. Remember, 1/3 power means cube root equals 8 to the 1/3, which is cube root of 8. This way you see your power of a power rule for exponents, and that's how you come out exactly with x. Remember that? Okay, pass these back. Let me give you a big check. I should write that you guys did a perfect job. Let me show everybody. Perfect. There you go. Oh, and I give y'all a check because you were almost perfect. And we'll send that back. Alrighty, so here we go. You need to use your book here because we don't want to sit here and graph all these library of functions. But these are the functions that you're going to be responsible for, knowing without spending any time plotting, the shape and a couple key points. And I'm going to point out the shapes and the couple key points. The first one, just like we just looked at, we're looking at the function f of x is equal to the square root of x. The square root of x, our key points are going to be 0, 0, 1, 1, and 4, 2. You want to always, when you sketch y equals square root of x, identify at least those 3 key points. Okay, square root of x. It talks about some of the properties, x and y intercepts. We don't talk about even and odd functions in here. This is an increasing function. And the reason it says it has a local minimum at 0, that's almost a little bit confusing. It's because we have a restricted domain here. Local really means within a neighborhood of the domain. So that's a little bit confusing. Local should be in an interval there. Okay, but you do have a restricted domain here, so I guess you could call it local. Okay, so add to your brain, I know exactly what square root of x looks like. Okay, the next one is x, the cube root of x. This is the next page. Y is equal to the cube root of x. All right? And they show you in this table how they just put in some points and came up with some key points for sketching this. All right? But your key points, when you get ready to sketch cube root of x, will be the easy ones. The 0, 0, which is right here, 1, 1, and negative 1, 1. Now, as long as you remember the graph's going to go like this, sometimes it's a good idea to include 8, 2, so that you see that it kind of curves off, and even negative 8, negative 2, which would send it down this way. All right, but basically your 3 key points are 0, 0, 1, 1. Oh, they didn't even put in negative 1, negative 1. And in your chart, negative 1, negative 1. Okay, everybody see how that shape is for cube root? All right, the next function that you're going to want to make sure you're good at is the absolute value function, but inside the absolute value symbol here is linear. Remember, absolute values define a distance, so your value always comes out to be positive when you take the absolute value of something. Absolute value of 3 is 3. Absolute value of negative 3 is also 3. It's how far are you from the origin. All right, so because inside the absolute value here is just like y equals x, you expect it to be linear. And when you plot your points here, 0, 0, of course, is a major point. And then 1, 1 and negative 1, 1, those are plenty of good points. When you have linear inside your absolute values, you're just going to have a V. You're going to recognize that as a V. Okay? I'm surprised that when they gave you the table here, they didn't include some negative values. When x is -3, the absolute value of -3 is +3. When x is -2, the absolute value of -2 is +2. And so there's your points right there. Okay, everybody good? All right. Without looking back in your book, use your finger and show me what y equals square root of x looks like. Y equals square root of x. Without looking back in your book, y equals cube root of x. What does it look like? I don't know if I can do that backwards or not. Yes, it is. It does look like a S, like you're in a hurry, a S. Okay, and without looking, absolute value of x. Oh, there you go. Didn't want you to see it. All right, so those are 3 functions so far that you want to be able to graph pretty quickly without plotting points. The next one's a piece of cake. Everybody knows that one. Y equals mx plus b. Split the page. All right, we're on page 258. The first one, this is just called a constant function. I've already asked you this in the last tape, I think. What is the graph of f of x equals b, y equal b? What does that look like? Horizontal line. Y equal 3, y equal -2. Horizontal line. That's why it's called a constant function. It's a horizontal line. The identity function is identity because, oh, here's the pictures. It's identity because when x is 1, y is 1. When x is 3, y is 3. The x is identical to the y. The y is identical to the x. It's called the identity function. All right. The next one, y equals x squared. We've been talking about this before. Everybody knows that's the graph of a parabola. Y equals x squared. All right, so what you want to put to your memory are 3 key points. At least 0, 0, 1, 1, and -1, 1. But be sure you realized it's curved, not like absolute value, 2 v's coming together. Because if you have x equals a half, when you square a half, you get a fourth. And that's why it flattens out more between -1 and 1, because you're squaring a fraction, which gives you a smaller y value. So your parabola is going to be flattened out. Okay? All right, the next function is the cube function. X cubed. Y equals x cubed. All right, your key points are 0, 0, 1, 1, and -1, -1. Y equals x cubed. It looks like a parabola, almost. It's going to go up a lot quicker than y equals x squared because you're cubing the x. But you can also, when you cube a negative, you're going to get negative values. So when x is less than 0, it's going to head down. Okay? And we already did the square root function with its 3 key points. And we already did the cube root function just a second ago with our, you told me it was a S. That's pretty good. Didn't even think about it like a S. Okay? And then the next one is the reciprocal function that you just graphed in the warm-up, 1 over x. Key point 1, 1 and -1, -1. Reciprocal function. And again, why is it called the reciprocal? Because it's just 1 over the x. Instead of y equals x, reciprocal of x is 1 over x. Okay? And then you already know the absolute value function. Looks like a v, absolute value function. And you are not required in this course for the greatest integer function. So you don't have to remember that one. All right? Now, I want you to turn to the exercises on page 263 at the top. The exercises on page 263 at the top. All right, what you're supposed to do is look at A through H and identify just by the shape which one of these is a constant function, which is linear, which is square function, whatever. So take a second and jot down what you think. Okay, now compare your answers to your neighbor. How'd your neighbor do? If your neighbor got it wrong, it's your fault because you should be helping them out. All right, ready? Okay, now not only are we going to give the words for what these functions are, we're going to give the equation. All right? As soon as you looked at number 9, what did you think of?
Square.
Square function. And what's the equation? Y equals
X squared.
x squared. So that's your square function. Everybody good?
Mhm.
All right, as soon as you looked at number 10, what did you think of the equation being?
Constant.
A constant function, and the equation is y equals
B.
b, some number b. Okay, y equal to b. It's constant. As soon as you saw number 11, what did you think of?
Square root.
Square root function. It looks like half a parabola laying on the side. What is the equation? Y equals
Square root.
square root of x. Y'all are so good. Number 12, I'm calling that a v. What did you think of?
Absolute.
Absolute value function. The equation is y equals
Absolute.
Value of X.
absolute value of x. You are so good. Number 13, what did you think of?
Identity.
A line, a linear function. What's
Y equals MX plus B.
y equals mx plus b? And you might have thought of an identity function, y equals x. It's hard to tell in number 13. Yes,
So those are two different functions then?
which
The
one?
linear and the
Identity?
identity? Are they two
It's-
different
it's-
ones or?
It's hard for me to tell if that's an identity because I can't tell if that has a slope of 1 or not because we don't
Okay.
know units. But if it went through the origin and it went up 1, 1, 2, 2, 3, 3, 4, 4, we'd know for sure it's an identity.
Okay.
But for sure, it is the graph of a linear function, y equals mx plus b.
Okay.
Is that good?
Yes, ma'am.
Yes.
Why don't they call constant functions linear?
Why don't they call constant functions linear? Constant function really is linear. I would say a constant function is just a special case of a linear function. Okay, number 14, what did that look like? Cube function, y equals x cubed. Excellent. Y equals x cubed. And 15, what did you call that one?
Reciprocal.
A reciprocal function. The equation is
Y equals 1x.
1 over x. Perfect. And number 16, because you guys taught me to look at it that way, it looks like a s. What is that?
Cube root.
Cube root function. I never looked at that as a s before. Okay, cube root function, and the equation is y equals cube root of x. All right, good job, good job. So we want to know if we see the shape of a graph, kind of what the equation is. If we hear square root, our brains want to go this way. Y equals absolute value of x. Our brains want to see something that looks like a V. Okay, so have some idea. All right, the next thing we want to do is what is called piecewise defined functions. And you're going to be working with piecewise defined functions quite a bit in your calculus, especially in the sections on limits. And all a piecewise defined function is some books will actually call it a multi-part function. Multi-part function just means that it's defined for different parts for different domains. So let's label it piecewise piecewise defined functions. And again, if you're using other books to supplement this, some books will call it multi-part functions. Okay, multi-part functions. And I'm going to start out with an example. I'm going to define a function f of x to be defined in two ways. It's going to be equal to the function x squared whenever my domain x is less than or equal to 0. And I'm going to define my function to be square root of x whenever x is greater than 0. Okay, the reason it's called piecewise defined is there's two pieces to this function in this particular case, and it all is based on the domain. All right, everybody has their own little way of doing it, and of course I think my way is the best, but you can do however you like. All right, let me set up my coordinate system. Labeling my axes, indicating my units, making good sketches, best I can. Oops, lost one in there. Okay. All right, now what I like to do, and I found that a lot of students like to do this because it's a lot easier, is they like to say, okay, if I were going to graph y equals x squared, my brain's going to go, that is a parabola. My key points are what, everybody? I'm just looking at y equals x squared, not with the domain here, but y equals x squared. What's my key points? 0, 0, and I'm going to do this lightly with pencil. And what else?
1,
1, 1, and
4, 2.
okay, no, 2, 4 you
2,
mean.
4, yeah.
2, 4. What else?
Negative 1, 1.
Negative 1, 1. Negative 2, 4. And so come in here with a little pencil and just graph y equals x squared. I hope that's showing up on tape. I'm just trying to do it lightly because this really isn't what I want my graph to be. But there's good old y equals x squared. All right. Now I'm going to come up here and it says you better only show the part of the graph where x is less than or equal to 0. Well, where on the graph is x less than or equal to 0?
The right side.
That's
Left side.
left side. Over here on the left side, this is x less than or equal to 0. So only show that part of the graph. So less than or equal to 0 is only that part of the graph. That's your y equals x squared part. Okay? So the reason I did that lightly in pencil is that just sort of gave me the idea quickly what the shape of the graph is, but I'm only keeping that part of the domain where x are negative numbers or 0. Okay? All right, now the next part of the graph says sketch the square root of x. As soon as you hear square root of x, your brain does what? Yep. 0, 0, 1, 1, 4, 2. So I'll just erase this part because that's really not part of the graph. So I'm just going to graph good old y equals square root of x. 0, 0, 1, 1, 4, 2, and the graph goes like this. My domain is x is greater than or equal to 0 for y equals square root of x anyway. Okay. Now, once I've got that drawn, I come back here and it says, but only use x bigger than 0, so don't be using x equal to 0. Well, x bigger than 0 starts at 0.000001, correct? So normally you would have put a little open circle here to show that x was going to be bigger than 0 and sketch your curve. But because the first part had already filled that in, my little open circle for the square root of x got filled in from the y equals x squared. Okay? All right, so when you're doing multi-part functions, if you will sketch the graph and then go back and just include the part that fills in the domain. Everybody good? Let's do a visual on this, everybody. Let's see how quickly we can sketch one from the exercises. Okay, I happen to be on page 263. 263. And we're going to look at number 36. 36. It's a piecewise define. It's 1 over x if x is less than 0, and it's defined to be the cube root of x whenever x is greater than or equal to 0. See if you can't graph that in 30 seconds or less. How's your neighbor doing? Are they good? All right, let's see what it's going to look like. All right, the first function to graph was y equals 1 over x. As soon as you thought 1 over x, your brain went reciprocal function. Isn't that what it did? Reciprocal function. 1, 1. Graph's going to come around like this. And -1, -1, and the graph's going to come around like this. Okay, do you see your graph of y equals 1 over x? Okay, but then you just come back up to your problem, which I jotted down right here, that I'm only interested in when x is a negative number, x is less than 0. So which part of my graph am I going to keep? The part that's in the third quadrant?
So it would never be in quadrant 2.
No, it will never be.
Even though that's
Oh,
negative.
right. These are x values that are negative, but when I substitute in these negative x values, the y values will be negative. So 1 over x would not have part of the picture up here. This is the graph of 1 over x for x less than 0. Does that make sense? Okay. All right. So now, everybody good on that? My key point was 1, 1. And then I had it approaching the x-axis in the negative direction and the y-axis in the negative direction. Okay, so we won't use that, and I have no eraser. All right, that's okay. All right, now we have to graph the cube root of x, and thanks to our friends, we know right away that's a s. I never thought of that as a s before. That is so good. 0, 0, 1, 1. And we could do a 8, 2, but the graph is going to go like this. And then it's going to go like this. Okay? It's going to go through -1, -1 also. Like this and like this. All right, but we are only interested in the part that is greater than or equal to 0. So we'll start right here with the part that's greater than or equal to 0. Here's my 1, 1. I would put my 8, 2 down here. And there we go. Okay? Almost looks like square root function when you leave it there. All right, would you say that this piecewise defined function is continuous? Oops, did I do something wrong?
Wouldn't that be an open circle?
This one says
equal to.
x is greater than or equal to 0, right? X greater than or equal to 0. So it would have to be closed when x is exactly equal to 0. Okay? All right, would you say that this piecewise defined function is continuous? That's not a word we talked about, but I'm interested. What do you think? Continuous? No, you usually think of something continuous that you can just keep on and on and on and on. But if I started to trace this, I'd have to then pick up my pencil to come over here. That's an intuitive way to think of continuity. All right, are we good? Suppose, let's play with this problem just a little bit more. I wrote it up here at the top. Suppose I ask you, what is the value of the function at 0? Find f of 0. How do you know which of these two you're going to substitute in? When x is exactly equal to 0, which one does it go with? Cube root. So I'd look at the cube root of 0, which is 0. Suppose I say, what is f of 10? F of 10. Which of these two am I going to substitute into? Cube root. I'm looking at a cube root of 10. Suppose I say, what is f of negative 1,000? Which one am I substituting into?
Reciprocal.
The reciprocal. That's 1 over negative 1,000. Okay, so just evaluating the function based on what it tells you the domain is here. Everybody good? All right, let's look at an application, and this apparently is a real application because they credit Sprint PCS as given the example. Okay, I'm on page 264, and we're going to look at problem number 45. Okay, this is an application of a piecewise defined function. And this has to do with cell phone services. This, at the time that they got this problem, a monthly cellular phone plan is $35. And this includes 300 anytime minutes. Plus, as soon as you start going over those 300 minutes, you're going to be paying 40 cents a minute. I've paid some powerful phone bills going over the minutes. I don't know about you guys. So anyway, the following function is used to compute the monthly cost to the subscriber. And before we start on this, aren't you just a little curious how they came up with this? Answer is that yes. I'm very curious how they came up with this piecewise defined. Instead of them just giving it to you. When people give you things, you want to know, how'd you figure that out? Is that true? Because somebody might give you a wrong answer, wrong information. You want to be checking behind them. All right, so what our goal is going to be is we're going to double check them on their equation here and see if we can make sure we know where this comes from. All right, so we're going to double check this. C of x. This is the cost, and it tells us that it is a flat $35 as long as your minutes don't go over 300. So the first part of this is pretty easy. It's $35, x represents minutes, as long as x is including 0 means you didn't use your phone at all that month, or you go up to exactly 300 minutes. Okay? But once you go over 300 minutes, because it says the additional minutes, remember x is number of minutes. Okay? So once it goes over 300 minutes, you're going to be charged 40 cents per additional minute. And somehow or another, they came up with a 0.40x minus 85. And you're going, where did that come from? I want to double check behind them to make sure they're right. So let's do our words. Whenever your minutes go over 300, what's your cost going to be? $35 plus all your additional minutes over 300, right, is going to be 40 cents. So it's going to be 40 cents times the extra minutes over 300. Whenever I tackle a word problem, I like to put in some words to help me see how I'm going to come up the equation. So if I'm over 300 minutes, I got to go ahead and pay my $35, and then it's going to be 40 cents times all the additional minutes over 300. So let's just put in a pretend. Let's pretend that you talked, we'll do pretend in red. Pretend. Pretend this month you did 400 minutes. Okay? So your cost would be $35 plus 40 cents times, how many minutes did you go over the 300? 100 minutes, right? So how are you going to use the 400 and the 300 to come up with the 100? Subtract 400 minus the 300. Isn't that the way it would work? All right, suppose you talked 600 minutes. Your cost would be 35 plus 40 cents. Okay, 600 minutes is, and you only were allowed 300. Didn't you go 300 over? So that would be 600 minus 300. All right, now I want you to help me figure out what the formula is going to be. It's going to be 40 cents. X is the number of minutes talked. What goes inside this parentheses right here? Say it again.
400.
X minus 3.
Well, X is varying. How many minutes I'm talking? This is my base. What's it going to be?
X minus 300.
X minus 300. Okay, so then you're looking at the equation they gave and you go, that doesn't look like that. So how would you make sure this is the same thing as what they gave you right here?
You add 30.
Yeah, just kind of clean this up and see what happens. We get 35 plus 0.40x, and 0.4 times negative 300 is minus 120. Okay. So when I simplify that, I get 0.40x. 35 minus 120 is negative 85. And that's exactly the equation they gave you. So when you see things like this, it's a very good idea you double check. You go in the stores and they claim they're having a 30% off sale off the original price. You better go in there and double check that you really are. Because I worked in a department store one time, and the people who were doing it, they were just going, oh, let's make that $29.95. Let's make that whatever. When they claimed they were having a 30% off sale, they didn't really go in there and do all the calculations. You need to be going in there doing your calculations just to make sure. Hopefully, though, in the last 40 years, they've improved, right? Okay, maybe they didn't have calculators back then. All right, so anyway, I just wanted you to see how you figure this out. Try using some words, use some examples, and make it make sense. All right, let's see what the rest of the question is. All right, so here's your piecewise defined. Compute the monthly cost. This is going to be a piece of cake. If you talk 200 minutes, what's your monthly cost going to be? 35, because it fell in the range from 0 to 300. If you use 365, which one of those equations are you going to use? Talk 365 minutes. The second one, correct. Just plug and chug there. How about 301 minutes? You're going to plug into the second. Everybody got it? All right, we have lots to do tomorrow. Graphing techniques, you really need to read ahead, and then we have some more applications in 2.8. Our goal is, in Lecture 4, we have got 2 sections to get done. Please read ahead and have a great day, everybody.